Okay, cool. So the last talk of the session is from University of Washington. Unfortunately, none of them could make it, but they are available online. So we're going to play the video of their presentation, and they will be on Zoom to answer our questions. The paper will be on resilient authentication architecture for federated private cellular networks. Yeah, go ahead.
Hello, I'm Curtis Heimerl. I'm here to talk to you about dAuth, Federated and Resilient Cellular Network Authentication. This is work led by Matthew Johnson, now at Starlink. So this project focuses on the long tail of internet connectivity. There are 5.4 billion people currently online, and we consider those to be people where the current models correctly work. And this work instead focusing on that next chunk, the 2.4 billion people who are covered by internet, have internet available to them, but are not online. And this is often for issues of affordability and other social factors, things like the internet content not being that interesting to them for a variety of reasons. Now, a big thesis here is to say that the people without connectivity are the people where current deployment models, this is stuff like AT&T, big MNOs, don't work. And so to cover those folks, we're going to need different approaches to get people online. Now, my research group has largely focused on community networks for a long time. These are local networks owned and operated by local actors to get local people online. And these change the network fundamentals quite a bit. You can imagine that they are cheaper. They use local actors. You might get free roof space, that kind of stuff, in order to cut costs. Similarly, they're significantly more capable in ways that are a little less intuitive. You can imagine that you can actually build a network for a specific population, let's say the unhoused, and target that network at them, something you could never do with a traditional MNO. Now, my group has been working in this space for a long time. On the far left, you see one of our first deployments in Indonesia, one of the first community cellular networks out there. On the far right, you can see our most recent network in Lahuktuk in the Canadian Arctic, where Spencer Sevilla turns a wrench on a roof, which is something we do a lot of in my group. Concurrent to all of this sort of long thread of community connectivity, industry has actually started to pick up some of these ideas. Now, what they're building right now is a space called private cellular networks. Now, this is functionally very similar. It's local organizations running small cell phone networks. Now, they're not really focusing on community use cases, but instead industrial use cases. This is stuff like factories. Factory may want to have really precise automation in place. And so they will install a cell phone network because it gives them better properties than a similar Wi-Fi network. Now, Grandview Research, an industrial research firm, expects compound annual growth in the space of 51% through 2030. So a big growing area for the future of telecom. And the reason for this is that there's been a number of technological shifts enabling these models. The big one is Spectrum. Citizens Broadband Radio Service, CBRS, provides high-quality 3.5 gigahertz spectrum to small operators. That's what we use. And I'll say in one of the densest urban environments with a lot of naval radar around, we see readily available spectrum even in a place like Seattle. Similarly, telecom has started to learn a lot of lessons from cloud compute, and we see that in stuff like commoditization of hardware, as well as open source software. And so we use both, Open5GS being our open source core network. Now, with these shifts and with this new industrial focus on private networks, we've started building the Seattle Community Network to take advantage of these private network innovations in this community network space. And so what we use is cellular technologies to build free and low-cost access networks throughout the Puget Sound region. This is for people who can't afford the internet, maybe can't afford devices, maybe don't know how to use the internet, and we want to get all those folks online. Now, we've installed a set of cellular sites throughout the region with the kind of community partners that we want to work with and enable them to help people get online. This is stuff like high schools, community centers, libraries, and hackerspaces. I want to note lightly that we also deploy Wi-Fi networks with some tiny home villages around, doing some IoT work, which hopefully you'll hear about in the future. So with these networks in place, we were thinking about what we wanted to do with this, and our big idea was to try to create a federation of these to get more people online. It looks a little like this. On the top, you can see a traditional MNO, and what you have is like an AT&T in red on the left and a T-Mobile in green on the right. And those have competing models of coverage, right? You pick which one you want to join based on their coverage and, of course, other properties. We want to do something different that we call cooperative cellular. The idea here is, again, let's say each one of these colors is one of our community networks, but instead of having them compete with each other, we want them to work together to provide connectivity. Technically, the way you do this is through roaming. You'll never have an AT&T user roam onto a T-Mobile network because they're competitors. But in our network, because they're actually all cooperating to get their communities online, the library would be happy to have a high schooler roam onto their network. And so socially this works, but technically through running SEN for a few years now, we noticed a problem. And the big problem is simply uptime. What we see is that because the kind of organizations we work with, small NGOs, are not very technically advanced, we see very rough uptimes. And in fact, no network in our network had 3 nines of availability. Now, this is a problem if we're going to be doing a lot of roaming inside of our network. So the core research question here that we're attacking is designing a roaming protocol that's resilient to the kind of transient home network failures that we see in SEN. So our key requirements for this system are, number 1, as mentioned, we're going to tolerate failures. Number 2, we're going to be an open network federation. We want other nodes to join our network, but those networks may or may not be trusted, and so we need to be able to handle them. Lastly, we need this to all be backwards compatible. It's going to need to operate with existing off-the-shelf equipment. Okay, great. So with these requirements in place, what are we going to do? First, I'm going to talk a little bit about cellular authentication to give some context of our solution. So the big thing we want to start with is recognizing first that a cell phone authenticates a user and a user authenticates a cell phone. And they do this through a shared symmetric key. So there's a key that's stored on the SIM card for the user and in the registry, the HLR, the AUSF in the core network. And this is a shared symmetric key put on both of them. This key is used to generate some messages. So you send an authentication request, then the attach request, then the auth request comes back, the user sends a result, and then they generate a session key on both sides and start their communication. The important thing to note here, and the thing we're going to take advantage of, is the fact that the session key itself is actually not sent over the air. It's different than on the internet. Instead, it's just generated mutually on both sides, and we're going to take advantage of that. So what are the challenges with this authentication scheme trying to build out a more resilient authentication roaming protocol? Well, first we note that cellular roaming already allows auth across networks, but it requires the home network to be up, and that's the problem we're trying to solve. The second thing we're going to note is that the shared symmetric key is actually really important. This naive solution here would be simply replicate that key among all the nodes in the network, but then those users could be spoofed. And it would be extremely problematic. So we need to make sure that we keep that network safe, or that key safe. So what do we do? So we're going to use 2 building blocks in order to build out our system. The first is proof of presence. First, the home network can actually pre-compute the expected result from the user. And instead of sharing that, share a hash of it. This means that any entity that can present the result for the hash is very likely communicating with the UE. So we're able to say that that user is who they say they are, and they are attaching to the network that the network is saying they are attaching to. The second thing we're going to take advantage of is threshold secret shares. This is an established primitive in multi-party cryptography. We take a key and divide it into n parts. We need to take an m of those, where m is some subset that we get to configure in order to reconstruct that key. Now, key shares can be used are used in our network to split the final session key across multiple backup networks. These backups are responsible for verifying the network's reputation, and so we get to configure how much we want that resilience to be in place. So it looks a little like this. We separate the authentication from the key, require a check-in proof of presence with multiple parties to get that final session key, and then that creates a verifiable evidence of activity in many places that we share back to the home network. There's a lot of words, so we'll go through it in diagram form. On the left, you see the blue network, which is the serving network. The green phone is trying to roam to the green network through the blue network. On the far right is the green network that shares this shared symmetric key for the green user in their home. In the middle are the backup networks. These are the ones that are going to help handle communication failures. The backup networks are pre-distributed with an auth tuple, a hash of the result, and a piece of the session's key share. So a user tries to show up on a green user shows up on the blue network here, and the blue network looks up the phone's home network and backup networks from a public directory, which we'll talk about a little bit later. Just imagine it's in the sky and it gives us this data. Now, if the green network is online, we go talk to them. There's only slight modifications here in terms of sequence numbers, but if they're online, we can just do normal roaming. If they're not online, the serving network instead requests an auth tuple from a backup, signed by them to verify that it came from a trusted backup. The backup validates the reputation of the serving network. We're only going to give this to them if we trust that the user wants to be on this network. And then they return the authentication message and a hash of the result. The authentication message is forwarded onto the UE, and the UE replies with the actual result. The serving network then presents a hash of the result and the result to all the backups, signed by the serving network. All backups store the signed key request to share with the home network later and validate again that the serving network is someone that we actually want the user to communicate with. The backups then provide the key shares to the serving network for them to reconstruct the session key and complete the handshake to the user. Later, once the home network recovers, the backups provide the auth proofs back to the home network to get refreshed key material. So then the home network knows that the green user attached to the blue network at this time, potentially for billing or other bookkeeping purposes. As long as n minus the threshold, which is configurable by us, the backups are honest and online, the user is protected from attaching to a network of insufficient reputation, and the auth results are returned to the home network to detect any suspicious behavior. Now, the only centralized information in this system, aside from, again, the shared symmetric key, is the infrequently changing directory. So, this is information that can be pushed to some DNS-like entity and cached and scaled on the scale of how often we change backups, which is very rarely. Now, an important note to note here is that dAuth scales differently than traditional roaming. Each of the networks can choose a different subset of networks to be their backup nodes. Here, the green chooses these, the blue chooses these, and the red chooses these. Now, you might choose these based on security ideas. These are the networks you particularly trust. You could also choose these for performance reasons, picking backup networks that are near you, expecting to see some locality benefits from the traffic. But the important thing to note here is that this leads to some kind of natural load balancing behavior. Instead of all the traffic going to authenticate to that main network, it actually gets distributed amongst a set of backups. And this is really important for us because we run a lot of low-cost networks with edge hardware. This kind of performance benefit makes it so that we can continue to run that hardware going forward. Note, many details are omitted from the presentation, so feel free to ask questions. We'll be there to answer them. So lastly, we want to evaluate the system. So we implemented a prototype integrated with the Open5Gs cellular core used by SCN, as well as other networks. And to test the scalability, we used a simulated RAN, UE RAN sim that can emulate hundreds of phones. It basically looks like real phones from dAuth's perspective. We started with simply making sure that this is backward compatible, and we took an off-the-shelf radio and an off-the-shelf phone and connected it in CBRS, and it all works. So the backward compatibility piece is there. For the simulated RAN evaluation, we did a network modeled on SCN's deployment. This is 12 auth nodes, including 2 edge nodes actually running within SCN. We wanted a mix of node types, capabilities, and different interconnect connections, because again, we deal with a fundamentally heterogeneous network. A lot of latency variations, but relatively low because they're all within Seattle. And then some cloud machines and some edge machines. We did 4 test scenarios, cloud and edge, and fiber and cable backups in order to do our evaluation. Lastly, we randomly sampled configurations of backup networks, although in practice what we expect is some optimization in terms of choosing ones that have specifically low latency in order to improve performance in the federation. We note that our baseline here is a standalone cloud core, which was just Open5Gs stock deployed in Azure. Azure chosen because it had the lowest latency to our test nodes. But it's important to note that dAuth in backup mode provides new capabilities relative to a cloud core. So this isn't really a direct baseline. We're not necessarily going to be faster than the cloud core, but we're going to do new things and enable new functionality. So what does it look like? It looks like this. You can see on the bottom is the time to complete the registration, and then left is the CDF of the samples. The dotted lines are the Open5Gs Cloud Core, and the solid lines are the dAuth in backup mode. Noting that, again, if we're not in backup mode, we are directly talking to the dAuth or the Open5Gs server, and so it would be much more similar to the Cloud Core, assuming that your core network was in the cloud. Now here at 20 auths per minute with 8 backups and a threshold of 4, what we see is that at low load, the simpler cloud core protocol is certainly more performant, but it's not robust to the kind of failures that we see in our network. And so kind of what we would expect. But if we bump that up to 200 auths per minute, we see something very different, which is that the Open5GS Cloud Core is actually less performant than the network that we're dealing with the break-even point in here of around 100 auths per minute. So essentially, because we're able to move that traffic across multiple backups, so specifically 4 that are going to actually be returning session key shares, we can actually improve the performance of the architecture. So great. I want to note that there's a lot more analysis in the paper, and especially in more generic performance elements, but this is what we wanted to bring up in the talk as we thought it was the most interesting of the set of results. Lastly, I want to talk a little bit through the Cloud Core. One thing that we want to strongly note here is that dAuth can run locally or in the cloud. And we expect cloud instances to significantly improve the uptime of our networks. A lot of the failures we saw were power and backhaul related kind of failures, which is what we've seen in community networks throughout our years of doing them. And so putting this system in the cloud instead would certainly reduce those. But I want to note that it will not remove them. There's significant issues like billing, like configuration that manifest in these networks with the kind of IT capabilities that they have as small NGOs, even in the cloud. Now, fundamentally, we have to support both edge and cloud because our partners prefer to run their services locally for autonomy and security reasons. But essentially, our argument is that this is fundamentally perpendicular to the design of dAuth. Private networks are foundationally independent. Like, that's the whole idea of a private network. If you have all of the radio elements talking to the same core network, that's just another MNO. So when you have multiple core networks, which is what private networks are, you have a distributed system. And distributed systems should be fault resilient. Because as you scale, even 5 nines means occasional failures at extremely large scale. And so we think that this system enables this. It gives you fault tolerance for a federation of these private networks and specifically solves our problem space. All right, thank you all so much, and I'm excited to take your questions.
Can we test if we can communicate with Curtis over Zoom? Curtis, can you hear us? Let's see. Should we see him? Okay, great. So Curtis, can you hear us in the room?
Yes, I can hear you. Can
Awesome.
you hear me?
Yes, we can hear you as well. Yeah, great.
Okay, great.
So yeah, if you have questions for Curtis, yeah, feel free to go ahead and ask, and he'll be able to answer. Yeah, go
ahead. Julie Jen from University of Minnesota, really nice piece of work. So I know the talk mostly focused on the authentication aspect, right? So wonder, because also you may also have some of the policy control because of different operator that may, I don't know, you kind of alluded to some of the policy one, right? So when you roaming, you may want to configure based on what the home network policy for the user. How do you actually, have you think about how you actually also do those things when our network is offline? You also cache some of the policies, like a credit remaining for the users?
So yeah, we definitely focused specifically on authentication here, just as a nice concrete problem to bring to a venue like SIGCOMM'.
Right.
I think stuff like trying to distribute a PCRF, the policy and control function, is actually brutally difficult. In our network, in SCN, a lot of these problems fall away because the network is free. And so most of those kind of functions are worried about billing in a large-scale MNO. And so we haven't had to address them, but it's kind of floating on the outside of the project as something that'll need to be tackled at some point. And I think it's actually a very, very complicated problem space. Similarly, something like handover has been on our radar in terms of a problem to solve with this architecture. So we're going to keep plugging away on it. We don't have any great answers at the moment, just because, again, we're like very action research oriented with the specific network that we're trying to support. And those problems haven't manifested there yet.
Right. So one additional question, since you kind of focus on the community cellular network, right? So for me, that the most important part is the cellular infrastructure. So a lot of complexity happening in the core side. So I was wondering, why could you just kind of building a consolidated cloud that work for all the different kind of essentially the RAN side of provider, right? So the RAN side, basically, based on the community, you want to place a sales station in a community space, but the core can be just running, say, Amazon Cloud. So you could potentially simplify having a one federated core, but then you have a kind of separate owned or deployed cellular RAN system. So have you thought about that type of architecture?
Yeah, I think this was lightly addressed in the core network discussion at the end, which, these organizations, the moment that those things start to get outsourced, it becomes like a separate organization running a new MNO. And there have been models like this. Traditionally in Wi-Fi, a few years ago, there was like, actually Comcast did a version of this too, where like you get little Wi-Fi hotspots and they all talk to Comcast, but you can install them in their house and stuff like this. That model hasn't worked. I think the financials and incentives get really confusing when there's this third-party organization that wants to install cellular gear in these locations. And so it actually being owned and operated and managed by the partner seems to be, for us, a critical change. Even though I agree, like the simplest way to do this would be some kind of distributed antenna system even, and just like, point it all at some central core network. But explicitly as research, we're trying to see if we can build something different. And I think we're making progress on it.
Great, thank you.
Sounds good. Have very quick question. Yeah, go ahead.
Okay, I'm Shashamon from NICTech. It is a good presentation. I just want to ask, is this simulation-based? And is it possible to be on the real world, not a simulation, to prove this authentication process that you have presented?
Yes, so there's actually some slides that we didn't get to present around that. One thing is that we did run this in SCN, like in our prod network a little bit, but at the end of the day, like that's a production network. And so with community partners, we're a little bit reluctant to like shove research code into these active networks with users. And so we haven't exactly done it yet. Okay. But that is definitely the plan, and has been something that we're working on. You can go see our GitHub of stuff that's been pushed and like trying to move us in that direction. We'd like this to be prod. We'd like this to be not, as an evaluation, but just as a functioning system, as a way to grow this federation, from us beyond to other areas as well. So yes, but it's just always that like research and practice barrier that exists.
Okay, yeah. Thank you everybody. Sorry, we already